Swayam Prabha. Digital India. Educated India.
So, good morning and welcome back to the NPTEL lecture series on classics in total synthesis part 1, and we have been discussing total synthesis of complex natural products, and in the last lecture we talked about the total synthesis of an anti-cancer agent called Taxol, and we will continue to discuss about more complex natural products and particularly anti-cancer agents. In 90s when we talked about Taxol, I also mentioned there were other complex natural products which were used as anti-cancer agents. There were at least 5 naturally occurring compounds which were supposed to be very potent against various cancers. The one which we already discussed was Taxol, which is quite complex, and the second one was Eleutherobin, which you can see that it is quite complex in structure, almost similar to Taxol. And the third one was epothelons. Here I am showing the structure of epothelon A, and there are other epothelons as well. So, this is a macrolide, and 2 more natural products which were also considered to be very good anti-cancer agents in 90s were dictyostatin and discodermalide. So, these are the 5 natural products where many synthetic groups were focusing on developing new methods, new strategies for their total synthesis. Okay, today what we will do, we will focus on one of them, that is Eleutherobin. See, this structure of Eleutherobin, if you look at, it has 3 rings. You can call it as A, B, C ring, and you have 2 side chains, one here and here. Okay. This was isolated in 90s from Eleutherobia species of marine soft corals found in Indian Ocean. Okay. And it was isolated at few milligram, and Fenical's group which isolated this compound proposed this structure. Okay. Of course, as you know, it was through various high field NMR studies they could propose the correct structure of Eleutherobin. Nevertheless, it is important from synthetic point of view to synthesize this compound and to prove the absolute configuration, because absolute configuration was not known that time. Then the second most important thing about this particular molecule is, since this was isolated from marine soft corals, as you know, marine soft corals particularly if it is in very sensitive region, then you cannot go back and then isolate more of them. So, from that angle also, if this molecule has to be made or to be made available for further medicinal and biological studies, and this could be done only through synthesis. So, from these 2 angles it was very important to develop a good strategy, and using this strategy one should be able to make not only Eleutherobin but also several analogues. So, as I said, many groups were involved in the total synthesis of Eleutherobin, but I will talk about 2 total syntheses. Today I will talk about one total synthesis reported by K.C. Nicolaou. Okay. And as I said, this was as active as Taxol. Okay. And it showed a high activity against various cancer cells, and it worked with a IC50 range of 10 to 15 nanomolar. Okay. That is quite significant. And the mechanism of action of Eleutherobin was almost like paclitaxel. Okay. So, this is another reason why many groups were interested in making this molecule. Okay. And also it worked against various types of cancer like breast, renal, ovarian and lung cancer. From the structural point of view, when the synthetic chemist wants to synthesize, it has 3 rings, set tricyclic core structure having a 6-membered ring, and the middle ring is 9-membered and the right hand side ring is 5-membered. So, all these 3 rings have 6 chiral centers, and the middle ring, 9-membered ring, that is a medium size ring, has 6 substituents. So, construction of 9-membered rings with 6 substituents is quite challenging, and overall in this molecule there were 10 chiral centers, and out of that 4 were coming from the sugar unit. And in addition to the core structure, that is the tricyclic ring, 6-membered, 9-membered and 5-membered ring, it also has 2 side chains, one at the northern hemisphere. So, that is an alpha beta unsaturated system, and down it has a arabinose system. Okay, these are the 2 side chains. So, a successful synthesis of eleutherobin not only should address the synthesis of core structure, but also an efficient synthetic route to the 2 side chains. And Nicolaou was the first one to report the total synthesis in 1997, and of course, as I mentioned, one of the major issue was to assign the absolute configuration of eleutherobin. So, he could successfully assign the absolute configuration based on the starting material which he used, and then further stereochemical elaboration. And the key reaction in the synthesis of epoxylon was an intramolecular addition of lithium acetylide, intramolecular addition of lithium acetylide to an alpha beta unsaturated aldehyde. Okay. That was the key reaction to make the 10-membered ring, and afterwards the 10-membered ring was converted into 9-5 bridged system. Okay. And of course, it was made easy since he started with a commercially available monoterpene called a carvone. And look at this structure. So, it is quite complex, and his retrosynthesis started with removal of this side chain first, that can be attached by simple esterification. Likewise, the other side chain, this arabinopyranose, can also be easily attached. So, the first disconnection of eleutherobin was removal of these 2 side chains, And the third important connection, as I said, first the starting material is from carvone, which has the same 6-membered ring with a double bond methyl group and an isopropyl group. So, it was very easy to identify the starting material, and construction of BC ring is quite challenging, because A ring is commercially available, you have to attach the B and C ring. So, he used 2-3 key reactions. One, as I said, the intramolecular addition of the triple bond. The triple bond later became double bond here. Overall, how he planned was, he first started with A ring, that is A ring at 6-membered ring, then he attached a 10-membered ring. Okay. So, the 10-membered ring is the combination of B and C ring. Then the 10-membered ring he converted into 9 and 5. B and C ring he formed from the 10-membered ring. That is how he made essentially 6, 9, 5 tricyclic ring. Okay. Let us see how he did this. First, he started with carvone, and as you know, the carvone has 2 double bonds. One is electron rich, the other one is electron deficient. So, one can selectively epoxidize the electron deficient double bond in the presence of electron rich double bond by alkaline hydrogen peroxide. So, alkaline hydrogen peroxide epoxidized the electron deficient double bond. So, now what one has to do is to reduce the electron rich double bond. So, that was easily done under standard hydrogenation condition. So, now you have introduced the isopropyl group, which is required for eleutherobin A ring. Okay. What is required now? Now you need to attach 2 substituents at these 2 carbons. Okay. 2 substituents at these 2 carbons. At the same time, you do not want this epoxide. What you want is a double bond, isn't it? Now we have basically we have protected the double bond as epoxide, but in the long run, before we go for total synthesis, you need that as a double bond. So what you can do, one can think about a transposition. Okay. So what he did, before that you need to introduce a functional group here. Okay. So if you treat with LDA, one can generate enolate and followed by quenching with formaldehyde. Now you could introduce a functional group at this carbon. Okay. So that is done. Now you have to protect the primary hydroxyl group, that can be easily done since it is primary hydroxyl group. Protection was done with TBS chloride, and after protection, now the next job is to, as I said, you have to introduce a functional group here and you have to remove the epoxide. Okay. So what he did, he reduced the ketone, with L-selectride stereoselectively to get alpha alcohol. Okay. Then this alpha alcohol was converted into a mesylate. Okay. So you got the mesylate. His idea was to cleave the epoxide, okay, to cleave the epoxide and bring this as an allylic alcohol. Okay. That can be done with sodium naphthalenide. When sodium naphthalenide will cleave this COMS bond, then it will open up the epoxide to get allylic alcohol. Okay. So now if you look at this structure, what one needs is, you need a functional group here and the double bond should shift here, and what you have is an allylic alcohol. Okay. This allylic alcohol, if you recall some of the rearrangements you have studied, allylic alcohols, if you attach appropriate substituents on the alcohol, then it can undergo a 3,3 sigmatropic rearrangement, that is Claisen rearrangement it can undergo. That way the double bond will migrate, and in the process you can also introduce a functional group. Okay. So with that idea, the Claisen rearrangement was done. The Claisen rearrangement you treat with triethyl orthoacetate, okay, triethyl orthoacetate in the presence of propionic acid, catalytic amount of propionic acid, followed by heating. Okay. So that will give you this intermediates, and this goes through this intermediate. On treatment with triethyl orthoacetate, it undergoes intramolecular Claisen rearrangement, and that will give you this gamma delta unsaturated ester, alpha, beta, gamma, delta unsaturated ester. Whenever you see a gamma delta unsaturated ester, the reaction which should come to your mind is Claisen rearrangement. So now you have an ester, and what you need is an aldehyde. So that can be easily done by reducing with dibol H. Okay. Dibol will reduce the ester to get the aldehyde. Okay. So that is a AB ring fragment. Okay. AB ring fragment, that means, so now you have to attach the C ring and then make the BC ring. So this fragment is made now. So what is required now? You have to make the two side chains. First you have to make the sugar fragment. So for that you start with arabinose. So arabinose, when you convert that into acetate, that per-acetylation will give you this tetraacetate. Okay. Now if you treat with phenyl thiol in the presence of Lewis acid, this anomeric acetate can be easily replaced by SPH. It is a standard reaction. So Lewis acid will coordinate here, and then this will expel the OAC. So you will get an oxonium ion, then phenyl thiol will attack, and you will get the SPH replacing the OAC. Okay. Then you can remove all the acetate in one part by treating with potassium carbonate methanol. So, you get the corresponding triol. If you look at this triol, these two diols are cis, whereas these two are trans. So, cis 1,2 diol can be easily protected as astronide. So, that is what being done. So, you protect the cis 1,2 diol here, and this can be written like this, it is just 180 degree, just rotate. If you rotate, and this is what you get. Why I have drawn this way was, this will be useful while you convert this into chair-like transition state, chair-like product. Okay. The chair conformation, when you want to convert this into chair conformation, then this will be more useful than this. So, that is why I ask you to rotate it by 180 degrees. Okay. Now, you see this is the chair conformation, and the diol is protected, cis diol is protected, and the equatorial alcohol, now you can protect it as PMB ether. Okay. Sodium hydride, PMB chloride will give you the protected PMB ether. Then you can also remove the astronide. You can remove the astronide by treating with para-toluene sulfonic acid and water. Okay. Now, both hydroxyl groups are protected as TBS ether, and this SPH can be removed by treating with NBS acetone and water. Okay. So, this should be converted into a good leaving group now. This should be converted into a good leaving group, so that when you make the core structure, of eleutherobin, then you should be able to couple. Okay. So, for that you treat with trichloroastronitrile, okay, sodium hydride and trichloroastronitrile, and this OH becomes OCNHCCl3, that is trichloroacetamide. Okay. So, this is the sugar fragment which we need to couple with their allelic alcohol. In the B ring you will have an allelic alcohol, that allelic alcohol you have to combine. Okay. So, we have made now the sugar fragment and then AB ring fragment, and the third fragment which we need is the alpha beta unsaturated carboxylic acid. So, this is a commercially available compound, and it can be also easily prepared from the corresponding aldehyde. If you have an aldehyde here, okay, then one can do Wittig reaction to get this alpha beta unsaturated ester, then hydrolyze the ester to get the corresponding acid, or in situ one can also add pivylyl chloride. So, to get this mixed anhydride. Okay. So, now you have the side chain of the northern hemisphere, and you also have the sugar fragment, and you have the AB fragment. What you need is you have to attach the C fragment. So, how one can do that is you have this aldehyde. Okay. So, this upon treatment with ethyl vinyl ether and tertiary butyl lithium. So, what does it do? When you have ethyl vinyl ether on treatment with tertiary butyl lithium, it will pick up this proton and it will generate this lithium species. Okay. This lithium species will add to this aldehyde, and you will get the corresponding allelic alcohol. Okay. And this is enol ether, is not it? This is still enol ether. So, the enol ether upon hydrolysis with acid, you will get the corresponding ketone. Okay. Now, as I said, you have to make C ring also, and the key reaction in the total synthesis of eleutherobin by Nicolaou is intramolecular addition of lithium acetylide. So, that means you need to add a triple bond. So, the triple bond was added in the form of acetylene magnesium bromide. Okay, you take acetylene and then treat with convert into the corresponding Grignard. This gives you the corresponding tertiary allelic alcohol. So, once you have this tertiary allelic alcohol, now what one can do, see the TBS which is protected, the primary alcohol can be cleaved with TBAF to get the corresponding primary alcohol. Okay. Once you have this primary alcohol, you already have a secondary alcohol and tertiary alcohol. Okay. All the hydroxyl groups can be now protected as TS ether. Okay. So, now you see you have 3 hydroxyl groups being protected as TS ether. Now, once you have this, selectively one can remove the primary TS ether. Primary TS is labile compared to secondary and tertiary. So, this is easily cleaved with PPTS and methanol. Okay. Once you have the primary alcohol, now you need to homologate. Okay. If you see the eleutherobin structure, you need an allylic alcohol here. You need an allylic alcohol here. That means this primary alcohol should be oxidized and then homologate. Okay. The primary alcohol should be oxidized and homologated. So, what you should do, you should oxidize this primary alcohol, and that can be done under very mild condition, so that you do not see the epimerization at the adjacent carbon. So, this is done by several oxidizing agents. What Nicolaou has used is tetra N-propyl ammonium perruthenate. Tetra N-propyl ammonium perruthenate. It is a ruthenium based reagent. In short, it is called as TPAF in catalytic amine, and the co-oxidant is NMO. So, that oxidizes the primary alcohol to corresponding aldehyde. So, once you have this aldehyde, then you carry out a Knoevenagel condensation with this ester, ethyl cyanoacetate. In the presence of beta alanine ethanol, you carry out a Knoevenagel condensation to get this alpha beta unsaturated ester, which also has a cyanide, So, now if you reduce this with the dibol, so you have 2 groups which can be reduced. One is cyanide and the other one is ester. So, cyanide, if you reduce with dibol, we know that it can be reduced to aldehyde. And if you take ester, and then treat with dibol, ester can be reduced to corresponding primary alcohol. So, in one part he converted the cyanide into aldehyde and ester into CH2OH. And if you look at again the structure of eleutherobin, this is what you need in B ring, and what you need is you have to somehow connect this, the triple bond and aldehyde. If you connect it, you will get a 10-membered ring. Okay. So, here he wanted to connect this with that aldehyde. Before that, he thought it is better to connect the side chain. Okay. It is better to connect the side chain to the primary alcohol. So, already made the sugar unit. So, this on treatment the TMS triplet, then you can see the sugar unit was attached to the primary alcohol. Okay. So, now all free hydroxyl groups are protected. If you look at this structure, all the free hydroxyl groups are protected. That paves way for generating anion here and then adding to the aldehyde. So, that paves way for generating anion here and adding to the aldehyde. So, this is easily done by treating with lithium hexamethyl disalicide. So, when you take lithium hexamethyl disalicide, it generates the acetylide, and under dilute condition the acetylide intramolecularly adds to the aldehyde to form the corresponding allylic alcohol. Okay. So, now what we have done, we have started with A ring, we have attached the sugar unit, and we also made a joint BC ring. Okay. So, now from the BC ring we have to really make B and C ring. Okay. So, BC ring is 10-membered ring. Now, we have to make a 9-membered B ring and 5-membered C ring. And for that, what one has to do, you have to reduce this triple bond, and this hydroxyl group, this OTS should be made as hydroxyl group, and that has to attack here. Okay. So, to do this, first we need to oxidize the alcohol here. To do this, we should oxidize the alcohol here. So, when you treat with desmartine peroiodinate, okay, desmartine peroiodinate is a very good reagent for oxidation of allylic alcohols, like manganese dioxide, PDC, desmartine peroiodinate is a very good reagent for oxidation of allylic alcohol. So, that gives the alpha beta unsaturated ketone. Okay. Now, when you remove the PMB group, because the PMB group is little bulky, so it is better to remove the PMB group by treating with DDQ, you get the free hydroxyl group. Then you reduce the triple bond to the double bond. At the same time, it is better to reprotect the hydroxyl as acetate. Okay. So, first the secondary alcohol was protected as acetate and secondary TS group and then tertiary TS group were removed and followed by the key reaction, that is the reduction of the triple bond, followed by the key reaction, that is the reduction of the triple bond. When you do that with Lindell catalyst, the triple bond is reduced to cis double bond. Okay. Triple bond is reduced to cis double bond. At the same time, the tertiary alcohol, okay, it can attack the ketone intramolecularly to form the lactol. Okay. So, now you can see the real core structure of eleutherobin, A, B, C ring. Everything is there. What needs to be done is you need to convert this hydroxyl into methoxy and also attach the side chain. Okay. So, these two can be done subsequently. First you treat this with PPTS methanol. So, PPTS methanol, what happens, this makes this hydroxyl as a leaving group and then the lone pair comes and then this breaks. That oxonium ion was attacked by methanol to form the methoxy. Okay. The oxonium ion was attacked by methoxy group, that is methanol, to get the methoxy group. Okay. So, now the methoxy group is introduced, the sugar unit is introduced, only thing left is the attachment of side chain in the northern hemisphere. Okay. So, already we prepared this side chain, mix these two in the presence of base, that gives the alpha beta unsaturated ester. Okay. So, you have this. Next, only one step, that is to remove the TBS group. There are two TBS group in the sugar unit and that can be easily removed by fluoride agent. So, TBAF treatment will remove the TBS group, leading to the formation of the natural product eleutherobin. Okay. It is a very important total synthesis and it was the first total synthesis of eleutherobin reported in the literature. And if you look at the key reaction is the intramolecular addition of lithium acetylide to the aldehyde to get the 10-membered ring. Okay. And then the hydrogenation of the triple bond to double bond followed by cyclization to form the 5-membered ring. These are the two key steps in the total synthesis of eleutherobin reported by K.C. Nicolaou, and overall this total synthesis was done in 27 longest linear steps, 27 longest linear steps. It is a linear synthesis. If you look at this synthesis carefully, it is a linear synthesis and with an overall yield close to 1%. So, considering the complexity of this natural product, an overall yield of 1% and starting with the commercially available monoterpene carbon is really a significant and then a classical one. Okay. So, with this we will stop here and then tomorrow we will talk more about another synthesis of eleutherobin, and this time the synthesis was accomplished by Samuel Danishevsky. Okay. Thank you.